Hello, this is Mr. White, and this video is on Newton's law of cooling. And yes, that is Newton as in Sir Isaac Newton. But don't let that intimidate you. Let me start by saying that exponential and logarithmic functions have plenty of real-world applications, whether it be looking at population growth as an exponential phenomenon, as we have recently, whether it be looking at the exponential behavior of compound interest, whether it be looking at the Richter scale, which is a logarithmic scale to measure the magnitudes of earthquakes, whether it be looking at the logarithmic scale of pH in chemistry. There are plenty of real-world applications, and I urge you to look out for them in your other classes because we certainly don't cover all those applications in math class alone. But let's jump right into Newton's law of cooling, which turns out it's basically an exponential model. And I'll warn you, brace yourself, it's a bit of a weighty topic, but ultimately it's just an application of all these things we've been learning all year long. So the quicker you can see the connection to things we've been doing earlier, the much more comfortable and confident you'll be with this topic. All right, let me jump right into a typical Newton's law of cooling type problem. Let's say we have a cup of tea, and in honor of English Mr. Newton there. We have a cup of tea and it's heated to 100 degrees Celsius, and we bring it outside on a chilly day when the outdoor temperature is 30 degrees. In 2 minutes the tea is cooled to 90 degrees. How long will it take for the tea to cool to 60 degrees? And I realize here just now that I forgot to put Celsius after all the degree measurements, but yes, you may assume they're all Celsius scale. All right, that's a typical Newton's law of cooling type problem. I'm going to ask, in fact, I'm going to require that you do this additional step, which I believe will help you get to the answer better and see the connection to what we've done earlier. I'm going to ask that you sketch and label a graph of how this temperature behaves with time. Okay, so I'm also right here in the video, I'm not going to require that you condense the words into a bullet point form, but I'm going to do that for the sake of this video. So my first bullet point is, let's take all these words and say that we are going to, as our first bullet point, come up with an equation, capital T, which will represent temperature, as a function of lowercase t, time. So rather than finding f of x, we're going to be finding capital T, temperature, as a function of lowercase t, time. The first piece of information in this text here, that the tea is heated initially to 100 degrees Celsius, that means that in this equation we come up with, I better be able to plug in time t equals 0 and get a capital T temperature of 100 degrees. All right, the fact that it is 30 degrees outside, that is going to be relevant. That is not the T's temperature, so I'm not going to put capital T equals 30 degrees, but I'll just say that the outdoor temperature is 30 degrees. Now, the T itself is said to reach 90 degrees after 2 minutes, so I will use the capital T equation and say that if I plug in lowercase t equals 2, I should get capital T equals 90 degrees. And finally, after we find the equation that describes temperature as a function of time, ultimately we will use that equation to find how long does it take for the tea to cool to 60 degrees. In other words, for this equation that we're going to develop, what lowercase t time do I plug in order to get 60 degrees as an output? Okay, so for the sake of this example, I've condensed it into bullet point form. I'm now going to scroll down and just leave the bullet points exposed. And again, my first request to you is to sketch and label a graph of how the temperature will decrease with time. And you will get to just use your common sense on this. Okay, so let's get axes out there. The vertical axis will be capital T as a function of our dependent variable or independent variable, lowercase t, time. And just use your common sense as far as what this graph ought to look like. We know that that's going to be our y-intercept. We've done enough problems like this recently. We know that's going to be our y-intercept, starting value of 100 degrees. And if you were to assume, based on this piece of information, that just because in the first 2 minutes it dropped 10 degrees, the T dropped 10 degrees to 90, if we were to assume that in another 2 minutes it would drop another 10 degrees, and that in another 2 minutes it would drop another 10 degrees, and so on, we would be assuming a linear scale. We would assume that it would be steadily dropping 10 degrees every 2 minutes, and just from the sketch, and just from our common sense, we know that's wrong. It's not going to just steadily pass the freezing point, and ultimately it would even defy the laws of physics by going below absolute zero. We know this doesn't make sense. So you could probably anticipate, and in fact I even said it earlier, that this is going to be an exponential model. Let me get rid of this. I said this would be an exponential model, but can you see what would be wrong with this? Can you see why that is not correct? Well, that implies that ultimately, as time goes on, we're going to be approaching zero. That means that the zero is in zero temperature, 0 degrees Celsius. This graph would imply that we're asymptotically approaching 0 degrees Celsius, and we know that's not true. So your common sense tells you that really this T is going to level out at 30 degrees. That's what our horizontal asymptote should be. So again, my claim is that in developing the sketch, this is going to help you come up with an equation much better than just using a formula out of the book. So I hope that you agree that this is just a kind of a common sense graph, and it's the one we'll be using. Now, if you're wondering, does this exponential model suggest that we'll only asymptotically approach 30 degrees but never reach it? Yes, that's what the model suggests. Again, these models aren't perfect. We'll just find, and in the real world, that this would work well enough. It'd be close enough, even though it erroneously suggests that the T never actually reaches 30 degrees. And that's a whole other interesting science discussion in itself as to whether that's a true statement or not. But anyway, let's proceed with this. I'm going to temporarily ignore this. We'll come back to that later. But at this point, let's turn to our basic function. This is one of those 12 basic functions. This is our basic exponential function that you learned early in the year. And let's think of what transformations do I need to do to this basic function to turn it into this function, capital T, that we want. Well, let me start by rewriting it in this function notation. Capital T is a function of lowercase t equals e, not to the x power, but the t power. All right? I'll start with that, and I think the first thing I'd like to do is to make this a decreasing function. It's supposed to decrease, not increase. So we can achieve that by flipping it across the y-axis. And you well know by now that you do that by replacing the t with a negative t. That's how we flip something across the y-axis. All right, we should know that this basic function, if I plug in 0 into the basic function, what do I get as an output? Well, anything to the 0 power is going to equal 1. So knowing that this goes through 0, 1, I'm going to suggest that we do a vertical stretch. Now, it would be an error to simply put in 100, and I hope you see why. If I put 100, yes, it'll vertically stretch it, and it'll go through the point 0, 100, which is what I want. But that would have it still asymptotically approaching the horizontal axis. And we said earlier that we don't want that. So we won't do that. What I ask you to notice instead is that this distance right here, that distance of 1 right now, corresponds on our other graph, it corresponds to this distance over here. Not 100, but it corresponds to the difference between 30 and 100. The distance between the horizontal asymptote and the y-intercept. So we want to vertically stretch it by 70, and then we will move it up. We'll translate it up by 30. Okay, I hope that's apparent. I hope we've done enough transformations where you say, yes, I see why that is. So again, we will stretch it by 70 vertically. Let's get rid of that 100. Let's vertically stretch it by 70, the difference between those two values. And then we'll move it up by 30. And that should successfully have us going through 0, 100. Whoa, I did that way too much. Let me do something like that. There we go. That'll go through 0, 100 as we wanted. And it will also asymptotically approach 30. So we're getting warm here. That was not intended to be a pun, but yeah, we're getting warm here in this Newton's law of cooling problem. Let's go ahead and address the one bullet point we haven't looked at yet. This one. T of 2 equals 90 degrees. I'm going to make the claim that we need a horizontal stretch or shrink to address that. It is very unlikely that if I plug in 2, I'm just going to magically get 90 as an output. So that 290, I don't know if I were to graph 290, it might appear on the left side of the graph, it might appear on the right side of the graph, but I'm going to make the claim that a horizontal stretch or shrink could make this graph go through that point. Now, I could horizontally shrink it, and it would look more like that. And it would still, notice that the horizontal shrink still preserves the y-intercept and the horizontal axis. That's why we're choosing it. We don't want to mess up the y-intercept or the horizontal asymptote, I should say. If it turns out that the point 290 is over on the right side of the graph and I need to horizontally stretch it instead, that's fine. Either way, a horizontal stretch or a horizontal shrink is going to result in this negative t exponent being replaced with negative kt, where k is our horizontal stretch or shrink factor. Oops. Okay? So let me take this equation. Pause and let this soak in if you need to. But I'm going to take this equation, move it down here, and let's go ahead and find out what k is. That's our next objective. And let me drag this bullet point down with us, because that's the one we need to pay attention to. All right. Let's use that bullet point to find what k is. All right, I'm going to do this rather quickly, because this should resemble stuff that we've done recently. This bullet point says that if I plug in t equals 2, lowercase t equals 2, I should get uppercase t equals 90. So I'm going to put 90 for the uppercase t and 2 for the lowercase t. All right, and again, rather quickly, I'm going to solve for k. This should feel like familiar territory. I'm going to subtract 30 from both sides. And I'm going to divide both sides by 70. And if I'm trying to solve for an unknown that's in the exponent, that means we use logarithms, right? Let's go ahead and reduce that fraction too. Let's make that 6 over 7. And I'm going to write logarithm base. What's our base here? Our base is e. Logarithms are exponents. What's the exponent? The exponent is negative k times 2. And that means that the 6/7 goes here. Okay, log base e is our special logarithm. Again, stop, pause, let this soak in if you need to. But relate this to stuff we've done recently. Remember, log base e is the same as ln. So just write ln of 6/7 equals negative k times 2. And finally, get k by itself by saying k equals, let's divide both sides by negative 2. And I'll put ln of 6/7 over negative 2. Okay, and this is the point where we grab the calculator. And on the calculator, if you type in ln of 6/7 over negative 2, you would get this value. Here's what you would be writing on your paper at this time. You should have, this is the equation that describes our temperature as a function of time. If I grab the calculator, I should be able to confirm a few points on there. Get the calculator up here. I've entered in that equation. Oh, let me mention this too. Go ahead and stow that k value. So we've talked about this enough where I expect you know what I'm referring to. Stow that k value as you see here, and then when you type your equation into the calculator, use the k value. Use that stowed value right here rather than waste time rewriting or retyping in that number. So again, I suggest you pause the video at this point and get this on your calculator just so you're absolutely comfortable with this. I have some recommended window settings here. Okay, let's check a few things. On our graph, if I trace to 0, I should get 100 because at time t equals 0, we had a temperature of 100, and there it is, check. At time t equals 2, we should get 90, right? There we go. Time t equals 2, we have 90. Now, finally, I hope you see why I entered this y2 equation. That's because if you remember way back when we introduced this problem, we were asked how long will it take for the t to cool to 60 degrees. So I'm okay with you on this type of problem solving that graphically. So you would do the whole second, calc, 5, enter, enter, enter. And there is our intersection point. So I know I kind of went through that last bit real quickly because it's supposed to be familiar stuff. But if it isn't, obviously come on by and get it cleared up. But that's our intersection point. This is the time where the temperature is supposed to reach 60 degrees. So you would put that on your paper and say at t equals 10.99, temperature equals 60 degrees. Or if you prefer, you may simply write capital T of 10.99, that's really our answer there, equals 60 degrees, okay? I hope I didn't lose you there. Again, please come on by, make the effort to come on by if anything in that didn't make sense. If you were to look in the book, Newton's law of cooling would be presented with this equation. I really want to de-emphasize that, but if you decide not to take my advice, if you decide to delve in this equation, please look at this as a vertical translation. Look at this as a vertical stretch or shrink, and remind yourself that this is our horizontal stretch or shrink. All right, your turn to try. Pause the video, please. Good luck. Okay, I'm trusting you've done your part. Let's see how you did. Here's the key points of this problem, and hopefully you got 67.36 minutes as your result.